in total.
This person join?
Yes, 3%.
On your
तापस रंजन साहू अच्छे
एक नया ज्वाइन किया उम्मीद बोल के
हैं
मासूम सुबह सुबह रोहित ने मुझे आवाज दे दिया आज
Okay.
नेक्स्ट क्लास के लिए
So very good evening to all.
कंटिन्यू ना
Very good evening to all of you. Today, this is the 6th lecture of NMR course, advanced NMR course. So we are discussing the solid state NMR aspects. So how to use solid state NMR technique to analyze, to understand the different structural units present in a solids and how it can correlate to different properties. So last class we have discussed something regarding how to predict the NMR pattern. How, for example, how many structural units are there of phosphorus, all those things we were discussing in the last class. It is possible to predict how many phosphorus are there with aluminium as near fixed number of aluminium and fixed number of gallium as near neighbors. And based on binomial equation, you can calculate different phosphorus structure on it. In fact, one problem we have solved in the class, that is nothing but for 50-50, aluminium 50%, gallium 50% solid solution, what are the different phosphorus structural unit which are present in the lattice, that we have solved it. And this also probably you might have also come across, gone through that. It is a quite simple procedure. So in aluminium phosphate, there are 5 aluminium phosphate and gallium phosphate solid solutions. We have 5 different phosphorus structural unit depending upon the number of aluminium and gallium as near neighbors. So then I have mentioned in one of the slides that please repeat the calculations. So repeat the calculations for compositions: 10% aluminium, 20% aluminium, 30% up to 90% aluminium. One by one, you can sit and you can calculate what are the different types of phosphorus structural unit, how its intensity changes in the P31 mass NMR. So for each composition, you can give a P31 mass NMR. And then we can discuss also. If you can solve that, it is well and good. I have also given as an assignment today. Today I have mailed the assignment. Probably by evening, these assignments will be getting uploaded. You may be 2 problems are there in the assignment. If time is there, then we will do after this class probably. Otherwise, maybe next class we can discuss that. So there are 2 problems in the assignment. One problem is on tin titanium solid solution, SnO2, TiO2 solid solutions. So here also almost same, principally same only. Here titanium is replaced by tin because tin also +4 oxidation state, titanium also +4 oxidation state. So part of the titanium is replaced by tin because this is a very common support. SnO2, TiO2s are very common support for a lot of applications are there, particularly TiO2 you must be already knowing. So we were working on SN1-X TiX O2 solid solutions. So let us discuss what are the information which we can get from this solid solution by using NMR. So here we have 2 NMR, actually all the 3 are NMR active nucleus. One is tin, another is titanium, and another is oxygen. The NMR active isotope of oxygen is O17, and titanium also there, titanium I think around 45 or something, I am not exactly remembering. But the element or the nucleus which we are probing is tin. Why tin? Because oxygen is a quadrupolar nucleus. Similarly, titanium is also a quadrupolar nucleus. For a quadrupolar nucleus, in the first class or second class, I have told there is a line broadening. Why there is a line broadening? Because there is an asymmetry in the charge distribution of the nucleus. So line should be unnecessarily broadened and we may not get any useful information. Of course, some information can give, but the broadening is too much. So the P line becomes complicated, the line shape becomes complicated and it is difficult to extract information from that, such type of complex line shape. So that is why we are going for tin, because tin is an NMR active nucleus with a spin half. The moment you have a spin half nucleus, it is easy to interpret the tin NMR pattern. So I just to show you the tin nucleus here. So tin is having a lot of isotopes. Out of these isotopes now, only 3 are NMR active. One is tin 115, which is a spin of half, but abundance is very small, 0.35%. Another one is tin 117, the abundance is around 7.6%, and another one is tin 119, the abundance is around 8.5 or 8.6%. So I can see actually the relative percentages also you can see here actually this. So these are the stable isotopes of tin, and out of these many stable isotopes, only 3 are NMR active, and these 3 NMR active, what happened, this we difficult to probe because first of all abundance is less, and these 2 are easy to probe, N117 and 119. And it so happens that whenever do 1119 NMR, you will have a coupling from 117. Similarly, whenever we do 1117 NMR, we have a coupling from 119. So these are, for example, if you take any material like SNO2, both tin are chemically same. So chemical equivalence is there, but magnetically inequivalent. These two nucleus. To take an SNO2, both isotopes will be there. In fact, all the 3 isotopes will be there. But as far as NMR is concerned, we get features of these 2 only. So here we have got a chemical equivalent and magnetically inequivalent things. So let us come back to the problem that was mentioned in the assignment. So I have mentioned the second problem I have given. The first problem in the assignment is this one. That is nothing but you can go through it today. Maybe by in the evening it may be getting uploaded, correct now? So you can download the PDF version and you can go through that. First problem is on this one. So here we probe tin NMR and find out how many near neighbor titaniums are there. Not even near neighbor, next near neighbor type, because near neighbor will be always oxygen, next near neighbor will be titanium. So let us see how many titanium next near neighbors will be there in such a solid solution. That is what I am going to discuss in this class. So in this class, if you see here, the tin is having 6 oxygen. You see here 1, 2, 3, 4, 5, 6 oxygen. These are called the near neighbors. Then we have got 4 here, 4 here. So total 10, and 1 here, 1 here. So 1, 2, 3, 4, 5. 5 here, 5 here. So total 10 tin as next near neighbors. There is a tin there which is at the body center of the above tetragon, but they are far away. Suppose you consider this tin and the above tin, they are quite far away. So they are not considered as a next near neighbor because their distance is quite far away. Similarly, below this tin, there is another tin which is the body center of another tetragon, below tetragon. But that is also far away, so we are not considering that. So as a near neighbor calculation, we have only 5 above. Next near neighbor calculation, we have only 5 above here. This side, or say right hand side, and 5 on the left hand side. So total there are 10 structural, 10 tin are there. So 10 tin are there means when you put titanium, what will happen? Each tin will be replaced by titanium systematically. So it follows a binomial distribution, and we can have how many configurations? You can think about that. In the case of aluminium gallium phosphate, because we have only 4 aluminium sites. So total how many? 5 are there. Total for configuration will become 5 because 1 is nothing but the individual compound. So if you take aluminium phosphate itself is 1, 4 aluminium. Then we have 4, 3, 2, 1 and 0. So what happened? We have got 5 configurations. Here, since we have 10 near neighbors, we will have 11 configurations.
Sudarshan, can I interrupt?
Yes, sir.
In this calculation,
Yes.
this information you need to have first, right?
Yes.
Yes. This information you get from crystal
structure. This is well reported. It's not to crystal.
You have to use crystal structure data
to understand. Explain, or predict the NMR line shapes. How many peaks will be getting? So basic understanding of the crystal structure is required depending upon the system.
Okay.
Aluminium phosphate also same thing. We got an idea how many, what are the crystal structure, what is, whether it's a tetragonal system or something like. So we have got 11 structure. N is equal to 11. So n is equal to 11 means what happened? We will have, this is only up to n is equal to 6. So you can go very well up to n is equal to 11 and you can get the coefficients. But the line shape, the peak positions, etc., you will get from how much is the shift in the chemical shift value. For example, in the case of aluminium gallium phosphate, we told that around 5 to 6 ppm shift is there with the replacement of each aluminium with gallium. Similarly, around 7 to 8 ppm shifts are there with each tin which is getting replaced by each titanium which is getting replaced by 10. So we have 11 configurations. You see, applying the equation which I have shown for aluminium gallium phosphate, you have to evaluate the different concentrations of 11 structural unit, and you have to give also the peak positions. So this is the assignment. Probably after this class, you will completely understand the problem and you will be able to do it. So you please go through the assignment, and then probably you can submit by maybe by 31st August or something, or the assignment. So the second problem in the assignment is nothing but forming a core shell particles. Last class we have discussed about core shell particles. Core shell particles, we know it is not a random mixing. At the interface, there can be random mixing. So assuming random mixing at the interface, same logic only you can calculate what is the relative concentration or what are the structural units possible at the interface, and you can predict the NMR line shape. So these are the two problems which I have given. So please go through that. So some similar problems also I can ask maybe in the examination. So this, please go through that. Any doubt or any clarifications, you can call me or you can mail me, and my number is given. So at any time, you are feel free to contact. So now let us continue. Let us now stop the discussions on assignment. Now let us continue again on tin NMR. So this information also will be quite useful. So this is the tin NMR of we have recorded at a spinning speed of around 5 kilohertz we have used, and this is recorded in our own laboratory that your tin oxide we have prepared, and then we have recorded the NMR signal. You see 1, 2, 3, total 4 signals are there. So which is the genuine signal? Because which one is the peak? Because in tin oxide there is only one tin environment. So we should get only a single peak. So how to confirm what is the isotropic peak? So the simple way is do repeated measurements with a different spinning speed. Instead of 5, increase to 7, increase to 8, increase to 10. So what will happen? The genuine peak, or which is nothing but the isotropic peak, does not change its position. Whereas all side bands, these are called side bands. So which we have, origin of which we have discussed in some of the previous classes. So you can use that logic, or I will just give you a brief maybe after 3-4 slides, because I will be talking about suppression of side bands. At that time we will discuss. But the side bands, the simple way to get rid of the side band is to do repeated spinning at a different frequency and identify which peak is the genuine peak. So here, by doing that, we observe that the peak around minus 604 ppm is the actual peak. Actual peak is tin characteristic isotropic peak, or which is characteristic of tin with 6 oxygen as near neighbors and 10 tin as next nearest neighbors. So by using suitable formula, which suitable programs which are available in the Google or in some websites, you can calculate from the sideband intensity what are the chemical shift anisotropies. These are the components. In fact, in solution, we don't have this component, because solution, everywhere the environment is same. We get only one value, sigma. Whereas in solids, we get 1, 2, 3, 3 components. This is also due to some assumptions. Of course, 9 components we should have, but based on an assumption, we will get only 3 components. So these 3 components are mentioned here. And once you mention here, another thing is that the difference between these two, also, there is nothing but delta sigma, which is nothing but sigma 33 minus sigma 11, is also a measure of the anisotropy. So these values we are getting because of the anisotropy. I will discuss it maybe after 2-3 slides again, this aspect, so that it will become more clear to you. So just I give an example. This probably some other case also I have shown in the previous classes. If you rotate it 4 kilohertz, you see only this peak is remaining at minus 604. And this peak is 604. Other peak positions will change. So by varying the spinning speed, you can get information regarding the side bands as well as the genuine peak. Or genuine peak is nothing but the, of course, side bands are also genuine peak, but only thing is it changes with respect to spinning speed, whereas the isotropic peak does not change. So this is the typical static NMR peak. So static NMR peak, you see how much broad it is of tin oxide. But you can get information beginning sigma 11, because sigma 11 may be somewhere here, sigma 22 may be here, and this is sigma 33. If you see here this table now, minus 557, minus 575, minus 678. So this sigma 11 and sigma 22 is more or less same. That is why this is an axially symmetric tensor we call. whereas sigma 33 is somewhat different. Of course, static NMR pattern give this information, whereas the magic angle spinning NMR gives the high resolution or the chemical environment of tin. So these are the differences. So before going further, I thought I will discuss 2-3 parameters called how sigma 11 and then what is delta ISO. This we have discussed also in the second class, because this we will be using this terminology. 4 terminologies are very important in the solid state NMR. Forget about this NMR pattern, because this I have written here. So the 4 terminologies, nothing but one is called delta isotropy, which is nothing but 1/3 of sigma 11 plus sigma 22 plus sigma 33. This I have discussed also sometime, just I am refreshing your memory. Sometimes delta 11 we can write also sigma 11, sigma 22. They are used either delta 11 or sigma 11 they can use. So delta 11, delta 22, delta 33 are the components of the chemical shift anisotropy. This we have discussed. In fact, in few classes back, I have shown how you will get the delta 11, delta 22, or sigma 11, sigma 22, etc. This is one parameter which we have to keep it in mind. That is nothing but the delta ISO. Very, very important parameter, delta ISO. Another important parameter which we have to give is nothing but delta, each component of delta YY. See, we are writing delta 11, delta 22, delta 33. So how to evaluate that? It is based on this expression. Delta IA is equal to sigma reference minus sigma IA divided by 1 minus sigma reference. Sometimes sigma reference is so small, so we say delta IA is equal to sigma reference minus sigma IA. There is a separate case. You can forget about that for the time being. So this is an expression for delta IA. Delta IA can be delta 11, delta 22, or delta 33. In solution, we don't have this expression. We have only one expression for delta. And then another second parameter is delta IA. This is also equally important, components of chemical shift anisotropy. Another parameter is anisotropy parameter. Anisotropy parameter, normally sometimes people write as capital delta aniso, or sometimes people write as small delta aniso. That is given by sigma 33, which is the highest value minus isotropy. So anisotropy, that is also an important parameter. When you say when you record a mass NMR pattern of a solid material, then we always say these 4 parameters. Isotropic, what is the isotropic value, what is the delta IA value, and what is the delta anisotropy, and what is the eta asymmetry. Those these asymmetric parameter. So 4 parameters are very important in the case of solid state. One is nothing but the isotropic chemical shift, and another is nothing but the components of the chemical shift anisotropy, and third is nothing but the anisotropy parameter. Why anisotropy? There is no, in solution there is no anisotropy, it is only isotropy. Since it's a solid, we have a difference of delta 33 minus delta iso. That shows if the value is higher, then we have anisotropy also higher. Similarly, eta asymmetry. Eta asymmetry is nothing but delta 11 minus delta 22 divided by delta 33 minus, it can be minus also, it can be positive also. If it is 1, I think we have discussed in the class. If it is 1, it is like a more or less like a symmetric tensor, like this one. It is more or less like a eta is equal to very close to 1, then it is more or less like a symmetric tensor. Normally, eta will not be 1, and only in some cases we get eta is equal to 1. So these 4 parameters, please remember me, in all solid state NMR patterns, we discuss these 4 parameters. Or from all solid state NMR pattern, these 4 parameters can be evaluated and compare. Depending upon the environment change, these parameters will be keep on changing. Now let us go back to the original position. So this we have discussed. So here also it will give an idea about sigma 11, sigma 22, and sigma 33, or delta 11, delta 22, and delta 33. They can be used either sigma 11 or delta 11. So you can see here, sigma 11 and sigma 22 are more or less very close, whereas sigma 33 is quite away. You can see minus 670. Similarly, you can see here from the line shape, sigma 11 and sigma 22 are nearly same, sigma 33 is square. This is more or nearly symmetric. This SiO2 is nearly symmetric. This asymmetry, it is eta is equal to, you can say asymmetry parameter is close to 1. Okay, now let me see. I have shown an NMR pattern of pure SiO2. Okay, SiO2 is having a lot of asymmetry in environment. Why this asymmetry is coming? Because you see here distances are different. I have told in the last class also, there is an axial oxygen and there is an equatorial oxygen. These 4 are equatorial oxygen, and these 2 are axial oxygen. Axial oxygen and equatorial oxygens have a different distance. So that will make the environment of tin slightly distorted. Similarly, And this near neighbor, next near neighbor also, if you see here now, 1, 2, 3, 4 are at the same distance, and the fifth one is at a different distance. And same is valid for this side also. So the totally the asymmetric environment is there. For local environment is quite asymmetric. That is why we get this type of side bands and we get a broad patterns like this. But if you take a compound like barium stannate, calcium stannate, barium stannate, strontium stannate are very important class of compounds. Technologically also important. These belong to a category called perovskites. Barium stannate is an example of a perovskite compound. So these perovskites are their highly symmetric structure. So once you have a highly symmetric structure, you see side bands are very, very less. Side bands are very, very less. You can see a single peak. Of course, spinning speed must be quite higher. One more thing you see here, there are you see two coupling peaks here. You see here, one peak here, which are symmetrically placed with respect to the central peak. And this is coming because of the coupling between tin 119 and tin 117 coupling. And in fact, we can evaluate the coupling constant also, which will be roughly in the range of around 400 or 450 hertz. In some examples, I have calculated the coupling constant. So this is also characteristic of the SiO6 octahedra, and this is also characteristic of the SiO6 octahedra with sideband. But here the nature of distortion is quite significant, or extent of distortion is quite significant, whereas here it is a highly symmetric structure. So that is why we get very sharp lines with a negligible, almost negligible sideband. There is no sideband here. So here also you can see here the tin is chemically equivalent but magnetically equivalent. Why magnetically equivalent? Because entirely different isotope. So gamma values are different. So that is why this is called as a magnetically equivalent. But chemically they are same. The environment around tin is same. Here because both of them has an octahedral configuration, SiO6 structural unit. But some of them are SN119 and some of them are SN117 and some of them are even SN115. But because of its low abundance, we are not seeing that coupling. We are able to see the coupling of these two. So this is nothing but tin NMR signal, 1119 tin mass NMR pattern of a typical compound called barium stannate, which is highly symmetric structure characteristic of the perovskite. So similarly, if you see all this perovskite structure, now we don't see any sidebands. The lack of sidebands indicates that the system is local environment is more symmetric. More symmetric means something you have to compare with somebody. So somebody or some other compound. So here we are comparing with the SnO2, and with respect to SnO2, we say the environment around tin in calcium stannate is much more symmetric compared to the pure tin oxide, although the coordination environment is same. And also if you go from calcium stannate, strontium stannate, barium stannate, you see how the NMR chemical shifts to higher and higher values. That you can always explain by a parameter called Z by R. What is Z by R? Z by R is nothing but the cationic field strength. So higher the cationic field strength, what happens? Polarizability will be better. Polarizability will be better. But here what happens? Z by R decreases if you go from calcium to strontium to barium. Your charge is remaining same. Calcium is 2 plus, strontium is 2 plus, barium is 2 plus. But barium is a very big nucleus or a very big atom. So once the atom size is big, the R value will be higher. So Z by R will be lower. So once the Z by R will be lower, it cannot influence, it will have a very poor Z by R ratio. So oxygen will have more electron density, so it will shift. Incidentally, the tin also will get more and more electron density and it gets shifted to more and more positive, negative, more and more negative values. That is why if you go from calcium stannate to strontium stannate to barium stannate, of course, electronegativity also decreases. We will get a more and more shielding. But you can see the lack of sidebands in this pattern. The lack of sidebands very clearly indicate that the environment around tin is quite symmetric compared to that of pure SnO2. I think I have made it clear because SnO2 we get a very broad peak or with a symmetry, an isotropic peak with respect and along with sidebands. Whereas that sideband completely disappears. Of course, spinning speed is slightly changed, but again, the sidebands you can see completely disappeared in this barium stannate, AbO3 structures, which are nothing but calcium stannate, strontium stannate, barium stannate, etc. So since I thought I have mentioned about a perovskite structure, because these are having a highly crystallographically highly symmetrical system. Barium stannate is a cubic system. So the barium atoms are at the corners of the cube. And the tin atom, where are there? Tin atoms are at the center, at the body center of the cube. And the oxygen you can see here. 6 oxygens are here. 4 are equatorial and 4 are axial. But these 4 equatorial and 4 axial bonds have almost same equal length. So once they are equal length, the octahedron formed of SN6 is perfectly symmetric. And once the octahedron is perfectly symmetric, we get relatively sharp lines with a negligible side bands. So you don't see any side band. It is very difficult to get information regarding the chemical shift and isotropy, etc. From this, because side bands, even though it appears, it gives information regarding the chemical shift and isotropy, such as sigma 11, sigma 22, sigma 33, etc. But this problem will be there when you have a complex solid with a variety of tin environment, then you will get side bands from all the tin environment. So then it will be difficult to find out which is the isotropic peak and which is the side bands. Actually, you may see in many of my lectures, mostly I am covering only the inorganic compounds actually. The reason being that in organic compounds, many times we can dissolve in many solvents and we can take a good NMR spectrum. Because why you go for solid, there are materials, some materials which cannot be dissolved, first of all. And the second is that some material, if you dissolve it, its properties will change. For example, materials like glass, zeolite, inorganic solids, perovskites, etc. If you dissolve in some acids or high concentration, its properties will change. So you will not get idea regarding the material property. Whereas in organic solvents, like many of the complexes, etc., many of the complexes or many of the organic compounds, the molecules remain same, does not change much, but you can vary the solvent and you can see to it that the molecule does not change, and you can get a reasonably high resolution NMR from many of the organic compounds. So in solids, many of the inorganic compounds, it is difficult to solubilize, like calcium carbonate or sodium chloride, etc. If you solubilize, then it can be solubilized, but the properties will change. You will not get the information. So that is why we are working on solid state. So preferentially that if you get a solid sample, if it can be solubilized in solvent, then definitely people will go for the solution NMR. It can be simplified. We can interpret in a much more better way compared to a solid. But we need to do solids also to understand, because certain solids like glass, for example, you cannot dissolve in anything. And we need to understand in the solid state itself, its properties. So that is why we are doing this solid state NMR. So that is why most of the compound, I will discuss maybe towards the end one or two few examples of organic compounds. But many of the compounds which we discuss for solid state NMR are basically inorganic compounds. Of course, nowadays a lot of reports are available on proteins which cannot be dissolved in many solvents. A lot of NMR studies are reported on proteins and other structures. Like polymer, for example, many of the polymer also you cannot dissolve. So people do carbon 13 NMR to get information. So this is a typical compound called actually a derivative of tetramethyltin. Derivative. See, this is a compound which is used as a tin reference. Tetramethyltin, which we put small amount of any powder sample you take and put small amount of the drop of the solution, and we will get tetramethyltin. And we can, this is assumed, this we assign zero chemical shift value. For example, in the case of phosphorus, we use 85% H3PO4. I forgot to tell, I think, in the class. In the case of tin, we use tetramethyltin as the standard. But many times we don't get tetramethyltin. So what we do is we put small amount of SNO2, and we know where the SNO2 peak comes. And then based on a secondary reference, we do the NMR pattern, because sometimes always getting a Me4SN is difficult. So this is somewhat a derivative of Me4SN. Me3SN 4 times C carbon. So you can see here the chemical shift value, you can see around 60 ppm or around 45 or 48 ppm, we can see 48.2 ppm. So interesting information here I want to say is that it's a single peak. Of course, we have used a decoupling also here. The decoupling I have not mentioned. Without decoupling, we will not be able to get good signal. We have also used decoupling spectrum. And these two peaks, like in the case of a barium stannate, there is no decoupling, just like there only a single pulse experiment, a single 90-degree pulse is applied, and we measure the decay of the magnetization inside a coil. So here we do decoupling, and after applying decoupling, we can very well see a single peak and due to symmetric side, not exactly side band. This is coming because of the coupling between tin 119 and tin 117, and this value is of the order of 305 Hz. So this is one compound. Then see why I have mentioned, I am again same thing I am mentioning here. A lot of people study organic compounds like polymers, like proteins, etc. There is a complexity also for solid state NMR of proteins, polymers, etc. There is some complexity associated with this organic compound. For example, let us say this is some sort of an amide linkages. If I remember correctly, CH3NH2 reacting with the CO group is there, and then an NH group is there. See, three color you can see here. One is green color, and another is violet color, and another is somewhat an orange color. This violet color is nothing but corresponding to a carbon attached to a benzene ring, phenyl carbon. Whereas this carbon corresponds to a carboxyl carbon. Carboxyl carbon we know is sp2 hybridized. Whereas this also we can say as an sp2 hybridized. Whereas this, which is nothing but a methyl group or a methyl group attached to the two functional groups or X or H, Y, it's a more electronegative group. So it is nothing but an sp3 hybridized carbon. So sp3 hybridized carbon is you can consider as tetrahedral symmetry, whereas the symmetry is lower in these two cases. So you can see how the difference in chemical shift value you see here. These are nothing but components sigma 11, sigma 22, and sigma 33. Similarly, this is sigma 11, sigma 22, and sigma 33. Whereas the moment you come to this group, which is nothing but an alkyl group or a CH methyl group attached with the X and Y, we have a relatively small value of anisotropy. See, the difference is a measure of the anisotropy, chemical shift anisotropy. So this is just to have a feeling of how a solid state NMR of this organic compound will look like. A typical example of carboxyl carbon, this is a phenyl carbon or benzene carbon, and this is nothing but the methyl carbon. So if you do a static NMR, you will not get anything. You will get a very broad peak. Even if you do magic angle spinning NMR, all these line shape you see here, very broad. It ranges from almost like around 225 to up to like 0 or maybe around 25. So you will get a lot of sideband for this carbon, sideband for this carbon, and for this sideband carbon, sidebands will be less because the difference is less. The anisotropies are quite high in these two cases, and you will get a lot of sideband. If you have multiple CO group and multiple CH2 group, then the situation becomes further problematic, and that is why not much investigations are there on this type of compounds actually, using solid state NMR techniques. Okay, let me continue. This one, let us say tin oxide I have discussed. Tin oxide is a typical compound, it's a very well-established, well-studied system, tin oxide. So many years, I think last 20-25 years, a lot of work is going on tin oxide because we all know that the tin oxide sensors are available in the market. So similarly, TiO2 also a well-studied system. People use it for various applications. So SnO2 TiO2 studied system. If you see in the literature, you can get a lot of tons of literature on this tin NMR. So now let us compare SnO2 and SnO. See what is the difference? Only the charge is different. In one case, tin is 4 plus oxidation state, and in another case, tin is in the +2 oxidation state. But the NMR patterns are quite different. First of all, the structure is quite different. SnO2, we know tin is having a tetrahedral environment, octahedral environment. We have discussed it, distorted octahedral environment. Whereas in SnO, tin is having a square pyramidal geometry. In square pyramidal geometry, what happens? 4 oxygen atoms forms the base, and one tin is existing at the apex position. So this is the typical, it's a layered structure. You can see all the red colored atoms are oxygen, and each tin is connected to 4 oxygen. So this is some sort of a square pyramidal, 4 oxygen on the base and 1 apical tin. So you see here, if you do a low spinning, this is a low mass. Low mass means very low spinning, means around 11. 11 is also high actually. In our case, it is 11. We were using 5 to 7, etc. But 11.8 kilohertz is a reasonably high. But normally that is called as a low magic angle spinning frequency. You see lot of peaks. So which is sideband and which is, because SN also tin is only one environment. We can see only one isotropic peak. And also you see the intensity of isotropic peak is quite low, because sidebands also overlaps because of the very high. And this NMR pattern is obtained by recording 3 different regions, 9 subspectra recorded and then added together to get this NMR spectra. So this I will discuss, this what of this green color, I will discuss it later. So this, if you go to higher and higher spinning speed, see, 43 kilohertz.
So this 9 Hertz spectrum means you are not able to excite the all.
All the regions, yes.
So
All
what
the,
is-
we take a small spectral width and record the side bands.
and then you add up.
Yes. Sometimes otherwise if you take a very big, sometimes folding happens.
Yes.
So which is side band or which is genuine peak, it will be difficult. So the small region they take and then record the spectrum. Actually, isotropic peak is only here, but here also signal comes because of this anisotropy. Isotropic peak or the peak of interest is here only, whatever marked with this yellow or orange color. Isotropic peak. These are all sideband, not genuine peak. They change with, for example, if you go to 43 kilohertz, sideband comes here. If you go to 55 kilohertz, it comes here. 75 kilohertz are very big number. So it is very difficult to get this type of thing because of you have to go for a very 1 mm rotor, etc. Then the amount of sample will become less because these are very high spinning speeds and the engineering requirements become very high to keep it the stable spinning speed. Actually, these data also have been simulated by measuring this delta ISO, delta IAN anisotropic parameter. And that is why for a particular value of delta ISO, which is marked by this red color, we will get a very good fitting. So that is why this plot is there. Eta asymmetry, we plotted against delta anisotropy. So if you plot this, then at a particular point corresponding to delta and eta, you get a better fitting, which is matches also with the experimental parameters. So you can understand how much difference is there between SNO and SNO2. The reason also, the reason being the SNO2 is having a lone pair of electrons. Whereas what is the configuration of SN? SN is nothing but 50, we know. Its atomic number is 50. So if you see the electronic configuration, we can say as krypton. Krypton is a filled shell configuration. Then we have got 3d10, 4d10, 4d10. Then we have got 5s2 and 5p2. 5p2. So krypton is around 36. Yeah, this is krypton is around 36 atomic number. 36, 4d10 plus 10 plus 14, around 50. So 5s2, 5p2. So 5p2 means the lone pair is mainly coming from the s2 orbital, and this s orbital is creating a lot of havoc around the tin atoms, and that is why we got considerably large number of side bands. So if you make a tin 2 complex, it will become really difficult to find out which is the side band and which is the isotropic peak. Of course, there if you go to very high spinning speeds, you can get this information. So that way, if you compare tin 2 and tin 4, the tin 2 is highly asymmetric structure with a lot of distortion in the local environment. So then, but there are studies on tin NMR, tin particularly NMR of tin 119, 119 tin mass NMR of tin 2 plus complex. So this we have taken from the literature. You can see there is this type of complexes are formed. Actually here, what happened? Tin is existing only in tin plus 2 state, but it can exist at two types. One is SnCl, Sn2 plus Cl plus, because one of the charge is not neutralized, so that is why plus charge here. Another is SnCl3. So here one excess charge is there. This type of complexes, one is a positive charge complex, another is a negative charge complex. They are neutral species. This type of complexes can be formed with this type of ligands. This type of ligand, these are called Lewis bases. So complexes of shift base with Sn2 plus. These are the ligand you can see here. So here M is nothing but tin 2 plus. Here also M is nothing but tin 2 plus only. But you can see here the lone pair you see here, the lone pair is here. This is creating all the problem actually, the lone pair. It is creating a lot of distortion in the environment and creating problem. So people have not dissolved this solid state, they have isolated. And in that solid state, they have recorded the NMR spectrum and they have reported the NMR spectrum of solid state. This is something like whatever I have written is there is nothing but a shift base actually. So complexes of shift base with the Sn2 plus ion. So you see the typical NMR spectra of this complex, tin 119 mass NMR spectra of this compound. Here M is nothing but tin 2 plus. Here is also tin 2 plus is there. Here is also tin 2 plus is there. So two different types of tin. Only two different types of tin. Still the complex, the pattern becomes so complex. One is, if you see here, MCl3, if you see here, if you go back and see here, see it is the structure is more or less simple because only M is there, 2 chlorines are 3 chlorines are only there. So this should not give much anisotropy in the line shape, whereas this should give much anisotropy because so many these organic groups are there, nitrogen is there attached to that. So this will give very high anisotropy, whereas this should not give that much anisotropy. So let us see how this pattern looks like. So here SN2 in SNCl3 is comes around minus 77.4 ppm. Minus 77.4 ppm will be somewhere here. This is called A type tin. A type tin. Then we have also got a B type tin. B type tin is somewhere coming here. You see here all the side bands are coming mainly because of the B type spin. So B type, somewhere B type spin comes here. B type tin 2 plus comes here. But one more tin is observed, B dash. Of course, the relative concentration is very small because in crystallography, what happened, even chemically, there are only there, two type of tin atom only is possible. In solution, probably we will get only two signals because one is for this tin and another is for this tin. But crystallographically, there are three tins are possible. And that is why we get one more signal that is called the B type, that is SN2, again SN2 only in this structure. So this is a monoclinic crystal system. So monoclinic system, triclinic crystal system, and this triclinic system normally multiple environments are present. So in cubic etc., cubic tetragonal etc., mostly only one component or only one type of environment only can be there. But if you go to a highly distorted, highly asymmetric systems such as triclinic, we can expect multiple cationic species or multiple sites. So that is why we see in solid state, we see three peaks. One at minus 77.4 ppm, which is characteristic of the SNCl3, which is nothing but this structural unit. And there are two peaks which are coming for this tin, which is crystallographically two different tin atoms are there. That is why we get two different peaks. But you can see the complexity, how complex it is. You can see the number of side bands. You may not be able to do proper experiment because if you have a low spinning speed, you need to go for very high spinning speeds. Then only you will get information. Because otherwise, many times side bands overlap. Side band of one site will overlap with the side band of another site. So information getting will become difficult. So people have simulated also, and which matches. And once you simulate, you can calculate parameters like delta ISO, delta II. And for delta ISO, we can get it by NMR, that experimental itself. And delta IA can be obtained from static NMR experiments. So once you fit all these parameters, we can get and we can match with what we get in the case of an experimentally observed pattern. So I told here, what I have told here that sideband is a menace. Sideband is a problem. We need to get rid of the sideband, and in the second class or third class itself, I have discussed how to get rid of the sidebands. We have discussed it thoroughly also. It is something called a rotational echo. Once you have a rotational echo, I think I have origin of sidebands I have discussed in the class thoroughly. So probably in the first or second lecture, I have discussed how the sideband arises. Sidebands are nothing but rotational echoes. I am just repeating whatever I have told at that time. So suppose you have a rotor here, a rotor is coming here, starting here, and it wrote half rotation is complete and one rotation is complete here. This is called a rotor period, time required for one rotation. Similarly, another rotor period, another rotor period, another rotor period, another rotor period. Let us say what happens in one rotor period. So I am just repeating whatever I have told just for refreshing your memory. So in one rotor period, what happened? Once atoms or spin packets or the nuclei rotate from here to here, coming back, complete one rotation, what happened? It will it will go through or it will feel a range of magnetic field because it is rotating. Correct? Na? So magnetic field is around the Z axis and this is along the magic angle. So by rotating, it will see a range of magnetic field. Whenever you see a range of magnetic field, it will create some sort of a distortion. So magnetization, which has come in the XY plane, has slightly started slightly degraded or slightly start defocusing. But after some time, you again come back to the same position at this point. So again, they refocus. The magnetization, which was initially defocused, will again refocus and you will get a peak. That is why appearing as a sideband. So this I have explained. So that is why we get sidebands. But if you are intelligent enough and if you do some pi pulses, if you calculate pi pulse, pulse width of a pi pulse or a 180-degree pulse, and if you synchronize with this rotation, then this type of echoes can be removed and you can get a sideband suppression. And this process is called a total sideband suppression, technically known as TOS. TOS is a double resonance technique. Why double resonance? We apply first a single pulse and then we apply multiple pi pulses. So multiple pi pulses can be synchronized with this rotor frequency. we call as rotor synchronized pi pulses. So these rotor synchronized pi pulses can be suitably applied by taking different delay times within a rotor itself, and we can cancel the components which are generating side bands. For example, if you see here, see I apply a 90-degree pulse. Okay, 90-degree pulse, rotor synchronized to 190-degree pulses to nullify the sideband intensities. Because sideband intensities we need to reduce, otherwise complex problems we will not be able to solve. We will be always have a problem, particularly in organic chemistry and particularly in heavy metals like tin oxide, lead oxide, etc. Lead is also an NMR nucleus. The problem is because of the lot of sidebands. So we apply different pi pulses. You can see, of course, phase cycling is also there. Probably those things might have discussed. I will not be discussing details to reduce the pulse imperfections and all those things. So 180-degree pulses you apply. You see, a rotor synchronized pulses you apply. So the moment you apply a 90-degree pulse, the magnetization comes in the XY plane, x-axis. If you apply in the Y direction, the magnetization comes in the x-axis. So it starts steadily defocusing. You see here. Now, if you apply pi pulses, what happens? So small there are other, this, whatever the main component or the isotropic component you can say it starts defocusing in this direction, etc. But by suitably applying 180-degree pulses, the sideband, what I say, the anisotropic components, not the isotropic component, can be allowed to fan like this. They can be allowed to spread using a suitable pi pulses, spread randomly. See here, some of them are spreading like this, some of them are. This is only isotropic component, this is a sideband component. See, this is coming like this, this is coming like this, this is coming like this, and this is coming like this. So by doing this, what happens? You can get an average effect. So as I mentioned, I am repeating you once again. See, once you apply a 90-degree pulse, both the isotropic spin packets as well as the anisotropic spin packets which are coming but because of the spin packets which are away from the rotor axis, they also will come. They also come to the x-axis. No, sorry, if you apply pulse along the y-axis, the magnetization comes along the x-axis. This magnetization include center band or the isotropic magnetization as well as the sideband magnetization. Correct, na? So this is nothing but what I have shown is isotropic magnetization, and this is nothing but the sideband magnetization. So isotropic magnetization starts spreading slowly, we can see here. Whereas by apply selectively rotor synchronized pi pulses, you can selectively defocus the sideband magnetization components. So that is why we get the sideband magnetic components, sideband magnetization component will cancel each other, and you will end up only with the isotropic magnetization component. Of course, there will be some loss will be there even from the isotropic component also, that we will forget it for the time being. But by using these pulses which are applied, rotor synchronized pi pulses can defocus randomly sideband magnetization. And the sideband magnetization defocus will lead to the averaging effect, and you will not see a peak corresponding to the sideband. So accurate determination of 90-degree and 180-degree pulses are quite important for this sideband suppression NMR technique. Because here we need to exactly find out what is the 90-degree pulse and what is the 180-degree pulse. So this can be pulse width program, or pulse width can be calculated by different experiments. So by using this pulse width, evaluated pulse width, you can apply a different delay times within a rotor period, and we can get rid of this sideband magnetization. So this can be, so as a result of this, we can only get isotropic or center band magnetization, and we can get rid of the sideband. So typical NMR spectrum from tin oxide, which we have recorded, which shows a single pulse experiment. You see here, this P corresponding to tin oxide at -604 with sidebands. And by using a toss, we can get completely suppressed sideband, but you may remember that you see here, there is a small peak which is coming here. So there is a small peak which is coming here, which is very, very difficult to see here. Of course, this peak is somewhat intense, we can see, but this peak is almost negligible. So this shows ineffectiveness of the pi pulse sequence. We need to further optimize it to get a better spectrum actually. So that is why there is a slight ambiguity, is that there is a slight miscalculation in the pulse width. That is why we see a very, very weak intensity peak because this matches with the sidebands. But this is a more or less a good experiment in which we can completely get rid of the pulse sidebands, and total toss or the total sideband suppression can be very effectively used to identify the different environment. Once you get the sideband, once you get rid of the sideband, we can find out whether is there any chemically different tin species formed. So that can be easily find out, because once otherwise the sideband will overlap with this peak, and then we will be finding it difficult whether it's a genuine peak or whether it's a sideband peak. It will become confusing and it will be very difficult to interpret. So why we have done this exercise is that suppose you want to analyze this solid solution, tin NMR of solid solution. If you just like that, if you record on NMR, single pulse NMR, we get a peak like this. But we do not know what are the different tin environments existing in this sample. Because if you change the spinning speed, these peaks are changing. So these are nothing but sidebands. But there is a genuine peak. There is a tin structural unit with a different number of titanium as near neighbors that is characterized by this peak. And in fact, this peak overlaps with this peak, and we are not able to get this information if you do a single pulse experiment. But if you do a toss or if you do a total sideband suppression, we get an individual peak at this position, which indicate tin structural units having varying number of titanium as near neighbors. So this information can be obtained by toss. If you do a single pulse experiment, this information you will not get. So this is nothing but tin structural unit having, I think, almost like titanium, around 6 or 7 titanium as near neighbors, which we will discuss probably in the maybe in the next class. Or this has been also theoretically also calculated how many titanium is there. But individual titanium we are not able to get. We are getting an overlap of many peaks. But if you do a single pulse, you will not be able to see that. We need to go for really a toss sequence. So similarly, toss may not be always required, but whenever the chemical shift anisotropies are higher, then we need to have a toss to get rid of this. For example, in systems like Y2SN2O7, which is called a pyrochlore structure. Pyrochlore structure, a lot of importance is there because pyrochlore is very widely used for nuclear technology and all, for waste immobilization and all. These pyrochlores are highly symmetric structure with the tin in the octahedral configuration. You see, like a perovskite structure, the pyrochlores also give a very sharp line, which is characteristic of a local environment, which is characteristic of the symmetric local environment and the negligible chemical shift anisotropy. From in such systems, the moment if you introduce an ion like yttrium or neodymium or any other ion like europium, we will be able to see a change in the line shape. So this spectrum shows how the NMR line shapes are different for a nano system. This is a nanocrystalline material and this is a bulk material. So nanocrystalline material, we see what happened. We have got a very broad line shape with a very large variation in the chemical shift anisotropy, whereas there is not much change in the chemical shift anisotropy of crystalline materials. I think this tin NMR I discussed today because I have given one assignment on tin NMR. Please go through the tin NMR assignment and you will be able to calculate how many tin with a next near neighbor titanium. So assuming it's a random distribution of tin and titanium, you will be able to generate 11 configuration for each of the solid solutions. And please derive these 11 configurations, and that is a part of the assignment. And you also draw tin NMR patterns, assuming there is a 5 or 6 ppm chemical shift difference between different tin structural units. Replacement of each tin with titanium give a negative chemical shift value of 5 ppm. For example, that can be very well seen here. This is nothing but a tin with 10 tin as next nearest neighbors. This is a tin with a titanium as next nearest neighbor, different number of titanium as next nearest neighbors. The situation is not simple as that of aluminium phosphate, gallium phosphate. Here the system is somewhat complicated, but you try to evaluate, and please feel free to discuss with me at any time. Please mail me also. So with this, I think today I conclude. What do you say? It's fine.
Yeah, it's fine.
So at any time, please feel free to contact me. You can mail me at any time. So next class, we are going to have a different system. So that is why I thought I will stop here.
Toss, we can suppress. Question.
Okay. Sir, by toss, we can suppress the sidebands. But how to know the composition? Yes. Yeah, it is true. Toss is only a sideband suppression. We cannot do composition analysis or we cannot get the composition of by doing toss. It is only a sideband suppression. And if you want to see the composition, you have to do multiple NMR experiments and compare with similar structured compounds. Then you analyze the NMR pattern. I don't know, is it clear to you? So composition, one has to do NMR spectrum with different spinning speed.
I think they can also speak. Hello, unmute them. Who is that person? You tell me.
Yeah. Please
Unmute and unmute.
unmute and speak. Hello? Please unmute and speak. So composition not possible to get by toss. Toss is only, what it does is only sideband suppression. For identifying composition, for example, if you have SNO2 or SNO, we have to do NMR and do a reference spinning speeds and get the isotropic peak position. And from that isotropic peak position, you can say whether it is SNO2 or whether it is SNO, or whether it is a barium stannate or whether it is a tin stannate or yttrium stannate. So one has to do like this only. Okay, we don't have speaker. Okay. Okay, I can mail you this answer if you mail me the email ID. Purpose. Any more questions? Okay.
So Sudarshan, how you are this thing 90-degree pulse, how you find out for solid state?
For state, what we will do, we measure the intensity of the signal. As a function.
What we do in the solution?
Solution, same only.
Same one.
We start from a very low value and keep on changing. We do D1 also, relaxation delay also. But first we will do D1, we will keep quite long, 10 seconds or something, and keep doing pulse width variation. And plot it, and then we can.
So it is the same way.
Same way only. 180-degree also we can do like that.
And this in toss spin, toss you are doing, so you have to use phase cycling.
Yes. Otherwise, pulse imperfection and interference will be very high. Toss phase cycling does actually, but this phase cycling program and all things I don't know. But phase cycling is a must.
See, you are taking the sample, the sample. Forget about the crystallinity, but you even in the powder also, you can have some kind of
amorphous nature.
Not homogeneity in the method also.
That also can broaden the line shape, sir. That also broaden. If you
adding to the line broadening.
Correct. That is adding to the line broadening. So next class, one more.
Sir, by toss we can suppress the side trends, but how to know the composition?
That I told you, sir, actually.
Okay.
We have to record variable spinning speed, find the isotropic peak position, and then compare whether it is SNO, SNO2, etc. because chemical shifts are different.
So it has a lot of correlation to the structure.
For a lot of correlation to the structure.
Lot of correlation to the structure. So until unless it means if you know the structure partially, it will be easy.
It will be easily figured. But straight away you will not be able to. You have to understand the first structure, and then only we can get information. But there are some structureless material now, like glass. So then this also will give information. Basic information we should have about the structures. So can we over they are in line now? Okay. Because I told can I announce that Wednesday there is no class. Monday I can announce that.
19. Monday.
Yeah, Monday.
We'll send email.
We'll send. Okay.
So send one email to. Unmute.
Should I announce now? Yeah. Student, sorry to interrupt. See, next Wednesday, there won't be any class. That is next Wednesday is 19th July. Solid state NMR lecture will not be there. So I will be coming on Monday, and then I will coming on Friday only. So Monday I will take 7th and Friday I will take 8th lecture. So please come. So thank you very much.
You tell Dr. Pal, na?